Coming to our final installment for the summer of this RQMP student seminar series. For our final speaker, we have Lena Engström, who splits her time between Tammy's group, Tammy Pereg-Barnea over at McGill, and William Witchup-Krempe at UDM. And Lena is going to tell us about some work that they've all been doing on the iridates. And one quick thing for logistics. So Lena has agreed to take questions throughout the talk. If you have any questions, either raise your hand in the participants menu or mention them in the chat, and then I'll moderate and try to interrupt Lena at an appropriate moment. So take it away, Lena.
Thank you. So my idea for today is to go through a bit about the PhD project that I'm working on, but a bit more specifically about this type of project in general. So I'm studying strontium iridates, which is a material that has been predicted to be superconducting, but we also know that there seems to be some more subtleties due to the multiorbital nature of the material, which means that we had to use different kinds of models. So what I will be doing, is to start out to describe sort of chronologically how these materials have been modeled. And we'll start out with the analogy of why they are considered to perhaps be superconducting due to being so similar to the cuprates. And then we will look at more why this effective model can arise and under what very specific conditions it actually could be valid. And I will then, in the end, a bit see how much time we have, go through more specifically what I'm doing in my project to sort of be able to tune the multi-orbital nature with some experimental effects to see if it could be more likely to have a system where you could have a superconductivity. So to go through, hopefully this as quickly as possible, we want to look at basically from the beginning how people have considered superconductivity in cuprates and to see why it's similar. So in undoped cuprates, you know that you have this insulating antiferromagnetic state. And then from experiments, so this is an experimentally derived phase diagram. Basically, you have experiments for the dope compound, and you look at experimentally with signatures, you can see for having different kinds of states. And now if we just want to consider the simplest model possible to basically start out in the undoped state, so we don't have an antiferromagnet, and see if we possibly could have superconductivity. All we want to search for is, say, antiferromagnetic order and superconducting order. And we will define these as having some kind of local order parameter which breaks the symmetry and is non-zero when we have these phases. So we want to look at the simplest possible model to sort of reproduce this phase diagram. So this simplest effective model that we have then can be this Hubbard model here, which is the T prime U V model. So we have a square lattice because the cuprates used like the iridates. It is perovskite structure where we have these basic quasi 2D layers of this square lattice. So what we consider is that we can have hopping between nearest neighbor sites. We also must include next to nearest neighbor sites because this gives this asymmetry between the electron dope and hole dope state, which we just know from experiments should be there. We then also want to include interactions to be able to see these kind of interacting orders. And we then, in this simplest model, have a Hubbard U, which is repulsing interaction on site between up and down spins. And here, since we just want to consider superconductivity in general, for this example, we just have a general V, which connects nearest neighboring sites with some interaction. So now what I will be doing generally in my models is to, when we want to compare, we can have different orders and different order parameters. We will treat these as simply as possible because we want to have a lot of points in a phase diagram. What we do then is just mean field approximation, basically saying that a pair of operators basically take the value of their mean. We just have a mean field background. This means that we can write down these order parameters and solve in this model just analytically for what the eigenstates are. And for each point in the phase diagram, we can plug in all the parameters and minimize the free energy. And we can see that the method of doing this is that from writing down the free energy, we can find that the minimized solution is found when we have a set of coupled mean field equations or self-consistency equations, which when all of these are fulfilled, we have found a minimized state. Now, to see that we have a prediction for superconductivity in the iridates, we can just compare the two materials. So this is the parent compound for a lot of cuprates, and this is the strontium 2 iridium 4, which I am considering. And we just need to know that they have the same structure. There are experiments and some calculations that just compare the band structure close to the Fermi surface. We can just fit these hopping and get some approximation of this U. So you can get these parameters. And then basically with this simplest model, you can just generate this phase diagram. Now, what you can see for the iridates is that there you actually have multiple bands, but if you just look at the ones closest to the Fermi surface, you can do the same fit, and you can basically see that all parameters are proportional to the cuprates, with one minus sign difference here. So the trick is then basically not to consider that they're different materials in a way, but just consider that it's the same model where you just plugged in different values that are just proportionally different. Where the difference with the minus sign here is that you have flip electron doping and hole doping, and due to having energy scale that is basically halved, you get that the orders only persist to about half the energy. But from this simple comparison, you can just say this material should be superconducting. And the first problem with this, among many, is that we know that this prediction only is valid for electron doping because we do have more bands on the hole doping side here. Now, why this simplest prediction has some problems is when we actually look at when it has been doped with electrons. So after this prediction had been made, chronologically, there has been experiments with doping these iridates. And we do see a decreased antiferromagnetic order. But the most promising for anything like superconductivity was done in 2016, where there was some kind of order that had a D-wave gap, which is what you expect from superconductivity in this case. However, after there's been done experiments up to even higher doping, they don't see any kind of superconducting order in any other way. So it's probably just some other density order. So this prediction, it could be sort of true, but it's not good enough to describe what we actually see in this system. So what I'll be working with instead is we will look at why this effective model arises and what the full model actually is here. So for this strontium iridium 4, we do have this sort of square lattice symmetry that I described earlier. Here we sort of have these iridium sites that are surrounded by these oxygen octahedra. A difference from the cuprate is that these are actually rotated with a much bigger angle, and that the magnetic moment in the ground state seem to follow this rotation much more strongly. And the full model, before we add interactions here, we want to consider 3 different orbitals. So these are, due to crystal field splitting, we have these 3 d orbitals that arise close to the Fermi surface. And from some DFT measurements that we are using, they can in the same way fit these different hoppings, but we then have to include hoppings in different directions and between different orbitals. We also want to have this rotation included. However, the main thing about the iridates is that we have this strong spin-orbit coupling, and that's where it gets interesting, because then we can actually split out a few of the bands from the rest with a magnitude proportional to the spin-orbit coupling. This means that we have some bands here closer to the Fermi surface, and this effective model describes them pretty closely at higher spin-orbit coupling. However, if we add interactions, we can see that it becomes more complicated, this picture. So we want 3 orbitals, as before 2 spins and 2 sublattices. So we will be using in a 12 operator basis. And now that we have several orbitals, what we need to consider with the interactions is that we no longer just have this Harvard U, but that we actually have interactions. Both that is this U, that is within the same orbital, we do have repulsive interactions, but we also have between orbitals that we have interactions. Here, the JH here is the so-called Hans coupling, which is fluctuation between different orbitals, and which tends to destroy some intra-orbital orders. And we also have this repulsive U prime that also is between orbitals. However, now when we have this more complicated model, what we want to ask ourselves about this system and why we're choosing this model is which order parameters do we actually want to include in this mean field analysis? Because before, when I just explained the simpler model, what we wanted to say about possible superconductivity was just a yes or no question: do we have an antiferromagnetic order, or do we have some superconducting order? Here, if we're considering multiple orbitals and just the magnetic order, is what I'm starting with here. We want more as the question, what are the different contributions from the different bands and from the different orbitals to the states that we see, and sort of how can we change that? So what we want to consider is that we can have a full magnetic moment, which is what we observe in experiments, which will consist of both the angular orbital momentum and the spin orbital momentum, which in this case we can have in all three directions. What's interesting is, since we have several orbitals, is that we can have these contributions from each of the orbitals. Like the spin arises from different spin within the same orbital, so we can have three different spin order parameters. But we also have this angular momentum, which is the same spin but mixes orbitals. And since we have a strong spin orbital coupling, we also need to include some order parameters that mix both of these components. And since we have a two-side basis, and we know that we will sort of have this canted antiferromagnetic state, is what we expect, we want to consider two sides that are independent. So we could have some staggered order, that is the difference between sides, and some net order, which is a net moment in some direction. Now this physically makes sense to look at these magnetic order parameters. The only problem is that we have a strong spin-orbital coupling, which means that we actually look at the eigenstates we get for the band structure. So this is the antiferromagnetic order. Since we have a gap, we can project the different orbitals onto this band structure and see that basically all bands is a mix between all these orbitals. So they're not really great states to describe processes close to the Fermi surface. So what we want to do instead is basically rewrite the whole Hamiltonian that we have, or at least order parameters, into a new basis that is more appropriate.
Lena, I have a question right here.
Yes.
Just to make sure I'm understanding the plots at the bottom. So is it the color of each band is the component of, is like the amplitude of the component you've indicated?
So you basically go for the eigenvalues, and you have some overlap between, what the original component is for that basis. Just
is this the probability or the magnitude of the amplitude or something like this?
So basically the probability.
Okay. Okay, thank you.
So the main point about going into this other basis, which we'll see here, is that we get different projection here. Instead looking at the basis that is the eigenstates to the spin orbit operator, we can look at this total angular momentum J basis. We basically have what we call M1, M2, M3 here, which is the two subspaces J equal 1/2 and J equal 3/2, where you can have this J Z, that's 1/2 or 3/2. And for example, we can see that the 1/2, 1/2 has equal contributions between the three different orbitals and different spins. And if we instead project eigenstates onto the band structure for this basis, we can see that, since we have a much lighter color here, that the 1/2, 1/2 basis pretty much solely describes the top bands here, which for the effective model that we considered before, we said that we could have one state that only described the top bands, and it seems to be this state mainly. But we do have some extra states, especially from the 3/2, 3/2 here, on one point of the Brillouin zone, where it comes close to the Fermi surface. So what we want to consider, if we want to consider how these different states contribute to the magnetic order, what's reasonable is to look at order parameters that instead describe pseudospins in these J bases and how they contribute to the magnetic order. So we have, for each of these three, we can have a different pseudospin magnetic moment. But what we also want to include, since we want to look at this more generally, is to have some kind of order parameters that mix these two states. So these don't physically mean too much in this perspective, but they do measure what the discrepancy is between just having a description of the individual bands and that have a mix between different J states. To see more specifically, I can show some results here. We know that we don't have an exact value for U and JH, the Hans coupling here. We just have some interval that fits with experiments for this model. We know that we should be getting this counted antiferromagnet. So this is at zero doping and just looking for this antiferromagnetic order. We still can have quite a few values of the Hans coupling that are valid. What we can see then, if we use this full model and consider different components, so we consider what different order parameters are that contribute to this state. We can see that the clearly most dominating one is from this J1/2 band, which are these pseudospins. So this is sort of what we expect because they are closest to the Fermi surface. However, we do have contributions from other order parameters, and we can change how much they contribute by changing the interactions. You can also see that by increasing or decreasing the spin-orbital coupling, which we have also some approximate value of, we can see that this band becomes more or less dominating. But what's interesting is that the extra order parameters that we see are not that we have these other bands that move closer to the Fermi surface or something like that, but it's the mixing between these different states that become larger, sort of indicating that this J1/2 state becomes less of a valid description, just projecting out that. So the point here is that this J1/2 model, which was used to predict superconductivity, works under a few very specific conditions. And these are that you can have these J1/2 bands, but they must be very separated from the rest of the bands. To the magnetic order, you expect that you only have this pseudospin here, J1 or J1/2 is the only one that contributes. And then this is determined when there's zero doping, and we are assuming for this simplified model that this remains the case even when we dope more. And this will also mean that the superconductivity that you see only consists of basically a pseudospin singlet in this J1/2 basis. However, when including one of these components, when we characterize what the antiferromagnetic state actually looks like, it seems like there should be other components that are relevant, and that this assumption that we can still use this model seems less valid. So now, what I'll be going through quickly, I don't think I have too much time left, is to show a bit what I've been doing in my project. So what I want to do,
if you want it, by the way.
Yeah.
No rush at all.
Oh, okay. Oh, yeah. Yeah, so the main thing I want to do in my project is to consider this full model. I'm still just considering the antiferromagnetic state that we want to characterize. But what we want to do now is to be able to find some parameter to manipulate what these different contributions are, either to move closer to this effective model or to find other interesting states that we possibly could find. And one parameter, I have been considering several, but one that has a big effect is to induce some strain on the system. So specifically what we're basing this on is there are a few experiments where you basically have epitaxial strain, which means they have to ground this compound on a substrate where the lattice parameters are either smaller or larger than those found in this strontium 2 iridium 4. This means that you basically change the underlying lattice of the structure. Now, what this means specifically for this material, and which basically had to be found from experiment because it's not obvious, at least from our models, is that the effect that this has structurally on the system is not that we actually change the bond lengths between the different sites in the square lattice, but we just rotate these octahedra closer or further from each other. So we change this angle. The effect that this has is that it does change the hopping between different sites, but due to us having these orbitals that are oriented in different directions, it means that it does change the hopping between orbitals in different ways depending on which orbital we are considering. So to see the effects that we get, we sort of linearize the effect the strain has on all of these hopping parameters that we were considering before. They have basically 4 samples of different strain, and we are considering this the general strain to be able to go both to higher values and to see what the general trend is. So we change both the hopping between different orbitals, but also this angle to be bigger or larger, be bigger or smaller. And the main effect we can see, like generally the trend, is that when we change the strain, increase it, we do increase these hopping parameters T. So they become larger, which means that we have broader bands. It doesn't affect the interaction at all. So the effect is that these the bands become broader, but the energy scale interactions remain the same. This means that as we increase the strain, we get broader bands and a smaller gap. It's harder for the interactions to sustain the order that we have. And eventually at some strain, we will get a phase transition where we no longer have an antiferromagnetic state. Eventually, since we have different hopping parameters for the different orbitals, it will mean that not only do we broaden these 2 types of bands, but we actually bring the J1/2 bands and the J3/2 bands closer to each other. So at some point, we actually get a Fermi surface with these J1/2 bands, but also that they become much more relevant for the state that we are considering. So to show some quick results for here, just the compressive strain, we do see that we do get a decreased antiferromagnetic order sort of linearly, which we could expect because we linearly change the energy scale. But we do see that the net moment here, since we have this canted antiferromagnetic order, remains pretty much the same and actually increases a bit since the moment seems to be coupled to having larger rotations. And eventually at some strain, we see that we have a phase transition, so we no longer have an antiferromagnetic order. So what we specifically can tell from our modeling this, is that we also can tell which of the different order parameters that actually are affected by this strain. And what we can see, and considering the net moment, but we can see that it's this J1/2 order that is mainly decreasing when the other ones remain pretty much the same. So this indicates both that we can go into a new state from having a large strain, but also with a smaller strain, we can tune which orbitals that are more important to the magnetic state that we see. So to sort of summarize what I've done with this problem and what the idea is, how to use this is that we do have this effective model, which is the one that predicts superconductivity, but it's only relevant for part of the iridate model and only under some strict assumptions. However, I've been considering the full multi-orbital model to sort of characterize which of these orders dominate and how we can change them. And then I've specifically been looking at some experimental effects that can have a large impact on which different components change when we increase it. And the way we can use this new component is basically that we can start looking for if we possibly could have superconductivity when increasing the strain. Because we know from the sort of general predictions for this type of superconductivity, that it does appear once you have a smaller antiferromagnetic order. So since we can manipulate the order and the different components, it's possible that we could see superconductivity in this regime, but it's also possible that we could change the contributions to which kind of orbitals that contribute in the superconductivity. So you might not just see the standard cuprate superconductivity, but it is possible in this model to possibly see some more exotic superconductivity. Yeah, and that's pretty much what I'm working on.
Great, thank you very much, Lena. That was really nice. Is anybody, we've got plenty of time for questions if anybody wants to start us off, otherwise I can. Okay, so I'll go. So you mentioned how the superconducting, like this little dome here in green, the superconducting dome there shows up as the antiferromagnetic order diminishes. But with the strain, you showed how you get this metallic phase. So would you expect there to be a difference in the type of superconductivity you get when you have this intermediate metallic phase versus when you come straight out of the antiferromagnet?
Yeah, possibly. Yeah, so the thing in the model here, I'm not considering any order except the antiferromagnetic one. So in the mean field, if you're not including the order parameter, you won't find order. So here it goes into just no longer antiferromagnetic, but just some kind of paramagnetic metal. However, what we see from mainly the band structure here, since we do bring these bands closer to each other, is that we now have contributions in the strain regime where we have this J-free half bands instead. So we have a contribution from both of these, and this is not an effect that you get from just doping. From doping, you just move this Fermi level line up and down. So then you can go into this whole dope state, but here you can actually have some electron doping and possibly have additional effects from this extra band that we couldn't see before.
Okay, cool. Thank you. Anybody else? I see Will has a question, I think.
Yep. So
Okay.
you guys hear me, yeah?
Yeah.
Yes.
Okay. Thanks, Lena, for a nice talk. I have a question about the basic experiments on this compound. So if you go back to the slide where you showed a D-wave form factor for RPES.
This one.
Yeah. So on the bottom right, you mentioned that it's possibly a density wave state.
Yeah.
In this RPES. So is that clear? Because I mean, from the paper, the Kim paper that has this plot, I mean, they suggest it's superconductivity just based on the similarity with the cuprate model and I mean the crystal structure, right? So can you maybe just clarify which experiments suggest that with this doping? Because this doping in that for that plot is special, right? I mean, it's this in situ potassium doping, right? It's not like your usual doping. So have people done this experiment with this type of doping in a broader regime? And I mean, yeah, I'm trying to understand why it's density wave versus superconductivity.
Yeah, so I think one of the main conclusions here is that they haven't done too much of the similar kind of experiments at further doping. Like this is a later experiment than this one. So in this one, they want to claim that it could be superconducting because that would be more exciting. But they also recognize that it could be some order close to superconductivity. That is some kind of density wave is also what they propose to be an alternative. And there hasn't been too much like similar work done here at higher doping. So it could possibly be, it's mainly speculation. Like there has been some pseudo-gap order that people have recognized. Sort of seem to appear, like even in this experiment, they go to higher temperatures and do see some more Fermi arcs. And that's also why they thought it was promising that it might be superconductivity. But but it's mostly based off, yeah, there aren't too many experiments actually concluding that it is a density wave in that way. It's more the lack of experiments that has been able to reproduce something like this, but stronger, or determining that it is superconductivity at higher strains, higher doping.
Yeah, so I guess for this in situ sodium dope, potassium dope, sorry, experiment, it's still up in the air, right? I mean, it's still not clear from the experimental point of view what's the underlying order that's doing this, if any, right? I mean, yeah. But
it's more that it's unclear.
Yeah, but I guess whatever order it is, it's still interesting, right? I mean, to have these arcs and then these B wave structure factor, that's still
I mean, it's
non-trivial.
Correlated with phase that appears, but it's the simple model doesn't seem to be good enough. So something about our model can possibly find some interesting state.
Mm-hmm. Well, thanks. I don't know if we have other questions, because I have another question, but if someone else wants to go,
I see in the chat that Tammy has one, if others don't, so I'll let you two decide who wants to go first.
Yeah, let Tammy, you said? Yeah, I mean,
yeah.
Please, yeah, Tammy, go.
Okay, sure. I just wanted to say, so we know that this is a huge problem in terms of computation, self-consistency of many coupled equations. Can you just give advice to people who might want to try to do something like that? How do you deal with that?
Oh yeah, I think, yeah, the easiest way of looking at it might be like, since we have to include the amount of order parameters that we think are interesting. So it's sort of about what kind of question we want to ask, I guess. That the main question we want to ask in this work is how big are the components from this effective model, basically, compared to all others. Which means that we could, if we wanted to do a slightly fewer order parameters that I'm including, you could just include these three, basically. And that would give you some information about if these bands have a larger contribution than these other ones. But sort of the question we wanted to ask as well is these bands a good description, or are there additional components that can sort of mix states, even if it's not obvious what if we could measure this kind of mixing. I think the question to ask is in the regimes where we know what's going on, for example, that we have one order parameter is large, that treating as few as possible is what we want to do. But here we specifically have a question about what a bunch of other order parameters do, and then we want to include a lot of them. So I think that advice is basically that it depends on the question we're asking.
Thanks.
Cool, thanks. William, did you still want to ask another question?
If no one else wants to go, I can ask a question.
Yeah, I see no other volunteers.
Okay. It's a fake question in the sense that I know the answer and Lena knows the answer, but maybe it's good for the other viewers to know the answer. So Lena, could you show the Fermi surface once you dope? Not dope, sorry. Once you strain the system, you get a phase transition into the semi-metal state.
If I can show it?
Yeah.
I don't think I have to ask here. I included.
No, well, that's okay. That's not a Fermi surface, but so you don't have any slides for the Fermi surface.
No, I don't.
But maybe if you go to the insulator bands, you know, it's kind of, you can describe what happens once you strain, right?
So what's basically what I showed with that just graphic that I pointed at is that we had these J1/2 bands, And we have these free half bands that are these two sets. And what we do when we induce some strain is that we basically both broaden the bands, so these will become much broader, as well as these, but also that we basically move these points closer to each other, meaning that when we have a strained sample, we will eventually, at high enough strain, end up with these bands going over the Fermi surface. We have these are the gamma points. We will actually have these free half bands, and at other points we will have these 1/2 bands. And when we go to higher and higher strain, we can have a larger and larger Fermi surface that consists of these additional bands. And that's sort of also what Ben's question was about, if we could see other kinds of states when we have strain compared to just doping, is that we can have Fermi surfaces where we actually have these additional bands. Yeah.
Thank you.
Great. I think we have time for another question if anybody has one. But if not, I'll take the chance to thank Lena again for a really nice talk, and thank everybody for being here for this talk and also for the whole series. This summer, it's been really nice to hear what people have been up to in RQMP. And hopefully we'll be back in touch before too long with another set of talks like this. But until then, I hope everyone has a great August.
And thank you for organizing. It's been a really nice series.
Thanks.